Hello, my name is Karthik Srikumar. I join you from South Windsor High School in South Windsor, Connecticut from these United States of America. Today I'll be presenting my project OATNet. It's a neural network architecture that is optimized for efficiency and its overall computation using ternary based weight decomposition and rank 1 magnitude approximation. So in the last few years, AI's become big. AI's become a household thing, but there's an environmental implication with it due to the immense energy consumption with these inefficient AI models, specifically large language models, which are natural language processing based models specifically for tasks of language and that required the semantic between words. Now, OATNet presents a scalable and environmentally sustainable alternative, reducing emissions if to be implemented without sacrificing model effectiveness, making it more corroborative in the real world. I looked more into the technical structure behind the large language model, specifically the transformer architecture, which was designed by Vaswani et al. In 2017 with the paper Attention is All You Need. It's a phenomenal paper. And they found that this transformer model using the multi-head self-attention mechanism was the way to go. However, this part, the multi-head self-attention, a section of the neural network architecture, which basically calculates semantic and relationship between words, relies on dense matrix multiplications of full scale with the input sequence length scaling the entire computation very largely. Current sparse architectures have been made to try to crunch down this computational bottleneck, but this is not very efficient. So the multi-head attention stands out as the primary source of computational overhead, and this needs to be resolved. Now, to ensure this truly works, I would begin with testing. Can these dense layer matrix multiplications be replaced to reduce energy use in LLMs while maintaining model performance? To do this, I would begin by providing a rigorous mathematical formulation to demonstrate that the solution I proposed would work. I would then ensure that I could reduce computational complexity, meaning it would be more energy efficient, but you still want it to perform competitive on industry benchmarks. Now, this was the proof of equivalence I had derived for the OATNet layer, which is optimized arithmetic via ternary networks. Now, we begin by taking the weight matrix that we originally begun with, and we would decompose it into its sign and magnitude components. The weight matrix is decomposed into its sign and weight components. However, we can approximate the element of the absolute value of the corresponding element in this weight matrix with a rank 1 magnitude approximation. Now, this allows us to retain key information while scaling in terms of direction and overall information. We were then able to use ternary weights, which is a weight of element using the elements of -1, 0, or 1. And what this would allow us to do is approximate the weight matrix for matrix multiplications using element-wise multiplication between the sign and the sign and the magnitude of the matrix. This would change the final computation done in this deep neural network layer as such. This would change the total amount of operations done by the optimized arithmetic via ternary network that we propose, which when tested would derive to the same final formulation that you would expect from the weight matrix. However, it would do it at a significantly less energy cost. Now, I would use these key structures that I talked about of the ternary weight structure, the rank 1 magnitude encoding, and using element-wise composition to multiply them to bring computational reduction due to the lack of dense matrix multiplications into real-world testing. So just to compare, the traditional transformer layer has these full precision matrix that have a high compute, a high memory of matrix multiplication. Our OATNet layer uses ternary weights with a ternary mask and defines it as the outer product of two vectors during our decomposition. And element-wise multiplication can then happen, which is significantly less dense. Now, this novel solution would be easily applicable inside the transformer block, as it would be able to go within the addition and normalization and go as this feed-forward neural network. OATNet's architecture is very soluble mathematically, but it was important to test this empirically to prove that the OATNet architecture was truly soluble. So for the so for my empirical methodology, I would begin by building the OATNet architecture, give it a pre-trained data set as well as text that is already tokenized. And this pre-processing approach would enable direct comparison of neural network architectures by isolating the computational efficiency from variations in input quality. Now, to create the OATNet model, I would use a large data set already on the internet, and I would be able to use pre-trained tokenizer or now to create the OATNet model, I would begin by data processing. The data would be a 10 gigabyte web text dataset, which is essentially internet dataset that does not have any passwords or key sensitive information inside of it. I would be able to test this model against other models that are public and open source. At the time of my research, the top models to test against were the GPT-3 models as well as the BERT models. We'll delve into future work of testing on to more models that have been released. Now, we would test on key metrics using some open source tools. We would be able to test how much energy the model is consuming as well as its performance on. Now, we found that OATNet significantly reduced the overall computation done during testing and inference by about 40% compared to models like GPT 3.5, which was the largest model in 2023, as well as the BERT-based model. Now, what's indicative of this is the fact that while it was also consuming less energy, which our math corroborated, we also saw the fact that it had a 12% better perplexity, which is a measure of essentially how well a model can predict words, which is what a language model like ChatGPT should be doing. Now, to ensure these results were credible, statistical testing I did showed that there was statistically significant evidence that the OATNet model was a lot better in terms of energy as well as performance than that of the models we tested it to. Now, this efficiency we can know from our studies came from our novel decomposition technique, as this would offer significant better ways of computation, allowing for more sustainable methods, which ties back into environmental benefits. By scaling this, we can use it at higher levels if it were to be deployed. Now, the reason for this is because OATNet captures the dominant signal directions with minimal parameter redundancy, optimizing token prediction probabilities, which thereby lowers perplexity and betters it. Now, we then conducted scaling analysis because for computational and cost purposes, I couldn't test this on a billion size scale. However, scaling analysis that was proven to be a good methodology showed that OATNet at the 8 billion parameter, which is what Mistral 8 billion was compared to, would actually perform less compute with similar accuracy to about 8.1 billion parameters, with about a standard error of about 348 million parameters, still in a high billion parameter. All of our testing methods shows that OATNet is a compelling alternative to the traditional large language models. It's more environmentally friendly while still performing at a level where it can be used competitively and has world advantages, as people want to use the best model. This optimized structure speeds up processing, and this gives significant environmental benefits. One limitation that we did find through our research, though, is that generalization to tasks that involve more reasoning, such as mathematical reasoning and coding, may be tasks that the model is hindered on due to the semantical way it is structured. Thank you so much for listening. Here are a list of some resources and references I used. Thank you so much for listening to OATNet. We are one step closer to a sustainable and more environmentally conscious way of doing artificial intelligence as a whole. Thank you so much. I'm Karthik Srikumar, and that was OATNet.